Good morning. I will be your substitute instructor this week, Monday and Wednesday. Today we are going to study the angular momentum. You have seen linear momentum, an object that is in motion that has certain mass will have certain amount of momentum. Momentum is a vectorial quantity. Since it has certain mass and certain velocity which has magnitude and direction, the multiplication of these two will eventually be a vector which will be pointing in the same direction as the velocity vector. So if I move in this direction, I have velocity, mass, that means I have momentum. Now, my momentum is reversed because the same mass is moving in the opposite direction. If one of you comes here and we start moving along this line and collide with each other at one point, we will transfer some momentum. And you have already seen that the linear momentum is a conserved quantity. So now we are going to study very same lines of logic in a slightly different context when we introduce the angular momentum. Angular momentum simply is the momentum in rotational motion. Up until now, you have been studying the dynamics of an object moving in a straight line or in a two-dimensional or three-dimensional space. In any case, it was moving in some direction. Now, today we are going to investigate what if the object is in rotation. In rotation along a fixed axis, so to say. Now, before that, we need to define a few important parameters. So what we are going to study today is the angular momentum. And the angular momentum is, once again, what was it again? Yes, what was it? So what was angular momentum? It's momentum in rotation. So don't forget, next time I'll ask you. So momentum in, that is the rotational momentum. Now, if there are two objects exerting force on each other, you can draw a position vector which will be in the direction, on the line that is connecting these two objects. To be more accurate, it will be on the line connecting the center of masses. Now, if an object, say a potato, is rotating around a fixed axis, say right here, we can put our coordinate axis in such a way that it will be right at the rotation axis. Here is x, here is y. And this is made to rotate. So take a unit element here, apply a force which will make this potato to rotate. can you do this experiment at home? Yes, why not? Take a potato, take a rod, put it through, not from the center, from any point, and push from one side of the potato, and it will rotate. The position vector is the vector that is right here, connecting the rotation axis. Now, for the time being, let's forget about what we are going to be investigating today, which is the angular momentum, and we know that there is the momentum in rotational motion. And let's focus on one particular quantity. But before that, let's remember the linear momentum, that is Newton's second law. You already know this very well. Which can be rewritten as simply mass times the velocity of the object. Now, we have the rotating potato rotating around a fixed axis, which we associated with the coordinate origin. And let's now, for the time being, focus on the quantity, which is the position vector r cross producted with the force. Now, why do we do this? Because we are going to see something important coming at the end of this operation. So without questioning too much at this stage, the cross product of the position vector with the force is simply the cross product of the position vector with this time-varying quantity, d by dt of m times v. Now, we are at a new stage where we are going to investigate this part, the right-hand side of this equation, for which you will use your intuition. This is the cross product of a position vector r with the time derivative of a linear momentum. So what I want to investigate to get to this form is the time derivative of the position vector with the linear momentum, which is m times v, where v is a vector, r is a vector, and these two vectors can only get into operation via a vector product, cross product. And this is the time derivative of this cross product, which operates on each of these terms. We will just simply use the simple rule of taking the derivative. We will take the derivative of the first one times the second one, cross the derivative of the second one times the first one. So the first term is r cross d times mv over dt plus d of dt of the position vector cross m times v. Does any of you have any difficulty in understanding what's going on here? This is the simple differentiation in the case of a cross product. Time derivative of the first one cross the second one plus the time derivative of the first one cross the second one. And we will need to be very careful with the order because R cross MV is not equal to MV cross R. There is going to be a negative sign if you were to write them in relation. So what do we get here? Let's focus on the right-hand side. What we have on the right-hand side, the very first term is what appeared on the right-hand side of R cross F. So we are getting somewhere. So the second term is what we are going to do a little more investigation next, is going to tell us something more. Now, what is dr over dt? It's the velocity. Therefore, I can rewrite it as simply the vector v cross m times v. Any objections? No, because dr over dt, the time derivative of the position vector is the velocity vector. What is v cross m times v? I tend to ask this part because there is a huge concentration here who tend to go out of control as soon as I go there. So what is v cross m times v? What is the cross product of a vector with itself? There's a vector here. There's another vector which is similar. This is v, this is m times v. If m is 2, this is twice as big as this one. So they both look the same direction. So what is the cross product of the two vectors if they are aligned, if they are lying parallel to each other? The cross product should remind you the sine of the angle between the two vectors, sine of 0, which is the case when the two vectors are parallel. Therefore, if two vectors are parallel to each other, their vector product or cross product will give you some of you say 0 here. How about the rest of the group? Why should it be 0? There is a whole bunch of terms there. Why should it be 0?
Because it goes on the same direction. The angle between vectors are 0, is 0, therefore C0 is equals to 0.
The magnitude of the resulting vector is proportional to the sine of the angle between the two. So the magnitude of v cross m times v is going to have V times M times V times sine of 0. And that will make a simple answer for us, because it is 0 since the vector V is parallel to M times V. Remember, V and M times V are related because they point in the same direction. M times V is just different in magnitude, but their directions are the same. So the first term, the second term here goes to 0 because V and M times V in cross product will give you 0. What's left here is what you were trying to investigate. That is, R position vector cross product with the force vector. So we have a good reason now to write that R cross F was R cross d by dt of M times V and since what you see here on the right hand side is the same as d by dt of R cross M times V, why don't we just replace it with and obtain that R cross F is simply the time derivative of a cross product between the position vector and the force vector. Remember, the position vector is the vector between the origin, axis of rotation, and the point where the force is applied. And the force is in such a direction. Okay. Now, here we need to identify certain important quantities. The left-hand side, the cross product of R and the force is what we call the torque. In other words, force in rotational motion. So this quantity here is what we would call the torque, and it's shown with a symbol N. It's a vector. Is it a vector? Yes, it is, because the cross product of two vectors will give you a vector. Please don't be confused with this N, since you must have used N for normal force as well. In this context, N is the torque, is R position vector cross product with the force. Now on the other side, we have the linear momentum and the position vector again in cross product. And we will define this quantity here as the angular momentum, which is shown with L. It's a vector, Why? Because, again, what you obtain, what you use to obtain it with is a vector operation between two vectors. So the resulting should be a vector. And it is simply R position vector cross m times v, or R cross the linear momentum. Now, here's the reason why we started with R cross F. Because in the end, we would obtain what we call the angular momentum. Now we put everything together to write that torque in rotational motion is simply the time derivative of the angular momentum, or the position vector cross the force vector is the time derivative of the angular momentum. Any questions? Now let's play with this a little bit. There is a force that makes an object rotate around a fixed axis, and that will correspond to yet another quantity which we called just now angular momentum. It's in a direction that is not in the direction of the position vector, that is not in the direction of the force, that's yet in a different direction. Now, if you know that there are two vectors, say, perpendicular to each other, the cross product of the two vectors will be in the direction that will be perpendicular to them both. So, if the position vector is in a certain direction and the force is perpendicular to it, the torque is going to be in the direction that is perpendicular to them both. So the torque that you will obtain by pushing an object and make it rotate is at the origin, at the rotation axis, in the direction perpendicular to these two vectors. You can easily obtain the direction using the right-hand rule. Remember that you curl your four fingers in the direction from the first vector to the other, and the direction of your thumb is going to be showing you the direction of the resulting cross product result. Similarly, angular momentum is a vector. How do we know that it's a vector? Because it's behind that panel. It is the vector product of two vectors. R, that is the position vector, and m times v, that is the velocity vector times the mass of the object. The cross product of two vectors will give you yet another vector in the direction that will be perpendicular to the position vector and the velocity vector. Okay, now let's consider a system that you are very familiar with. Here is the sun, not far from here, only about 150 million kilometers away. And right here in its vicinity, there is the Earth. And Earth is in motion around the sun in an almost circular orbit, which is completed in 1 year, which is what we call a year. One full rotation of Earth around the sun. Now, why does Earth move around the sun? Or why should Earth move around the sun? Well, there must be a force between the two. And in this case, it's the attractive gravitational force that Earth and Sun system feels. So there is a force which is a central force. Now, you have seen earlier conservative forces. Now, we are going to investigate something new. A force can also be central. If a force is spherically symmetric, it's usually a central force. The sun is a gravitational object, gravitational body. We will study the gravitational force on Wednesday. And it has a gravitational force field that is spherically symmetric around it. So the gravitational force is a central force. So what is special about the central force? Or can there be any force that is not central? Well, there can be, of course. If you have a racket playing tennis, if you hit the ball with your racket and give that ball a little bit of spin, then the force between the ball and the racket will not be a central force. So, non-central force, let's leave them aside and now look at this case. Where is the position vector? Earth is in rotation around the sun. Sun is almost fixed. Sun doesn't rotate around the Earth. So we can assume that sun is stationary and Earth is in rotation. So the position vector is somewhere in the line joining the center of masses. Right there. And the gravitational force between the two is lying parallel to the central, the position vector. It's parallel, in particular, to be correct, it's anti-parallel. They are opposite to each other. Therefore, in this case, in the case of a gravitational force, force and the position vector are parallel. So what does this imply? If the two are parallel, what's the outcome? Not you this time, although you are going to give the same answer. R cross F has to be 0. Why? Because the angle between them is either 0 or 180 degrees. Sine of 0 and 180 degrees are both 0. So this is the first part of the investigation. Then R cross F is 0 always? No. If the force is central. This is fine, but there is more to understand from here. Now remember that R cross F, we have right down here, is the time derivative of the angular momentum vector. For a central force, R cross F is 0. That means the time derivative of angular momentum should also be 0. Because these two quantities are the same, and this is the case only if the force is central. Now here's the important conclusion. For a central force, R cross F is 0 because they are parallel to each other, but more importantly, the time derivative of angular momentum is 0. In other words, angular momentum does not change in time. Whatever angular momentum you have now is the same 10 hours from now. Just stay and keep measuring. You will measure the same thing as long as the force is a central force. So our conclusion is angular momentum is conserved for central forces. You will see more examples of central forces in the later stages of the course, such as the electrostatic force. But you will also see some non-central forces, such as the magnetic force, again coming up later in the course. As long as the force is central, the angular momentum is going to be conserved. So just like the linear momentum conservation, we know that linear momentum is conserved if the net force acting is 0. If there is no extra external force acting on the system, the collision should conserve the linear momentum. If it's an elastic collision, you can also conserve the kinetic energy. That's more to it. But linear momentum should be conserved no matter what, as long as the net force acting on the system is 0. Now there's a condition. Linear momentum is not conserved forever. If there's external force, the story is different. Just like that, or similar to that, if the force is central, then the angular momentum has to be conserved. L vector now is the same L vector in 10 hours or 20 hours or 10 years, as long as you preserve the central force. Any questions? Now, L is a vector. Angular momentum is a vector that comes with a magnitude and direction. So if it's conserved, you should not only conserve the magnitude of it, and also its direction. You cannot just conserve its magnitude, but not its direction. You should conserve the both magnitude and direction quantities. So this is going to be something we are going to do next. But before we go into those directional arguments, in the last 10 minutes before the break, let's consider the Earth-Sun system a little closer. Now here is the Sun again. Here is the Earth. Here is the position vector r. What is the angular momentum of the Earth? We know that L, angular momentum, is R cross m times v. R is the position vector, and Earth is in motion around the Sun with constant speed, but its direction is always changing. The position vector is perpendicular to the direction of the velocity vector. Therefore, we can write for Earth, it's the position vector, that is the distance, 150 million kilometers, in the direction from Sun to Earth, cross mass of Earth times the velocity of the Earth. Now the magnitude, let's put this axis of rotation into XY coordinate system. Here is X, let's say here is Y. The magnitude, let's determine this very quickly, is the distance between the two, that is the magnitude. Forget about the direction. Direction is always changing as Earth moves around the Sun, times the mass of Earth, velocity of the Earth, times the angle between the position vector and the momentum vector. And what is that angle, theta, between the velocity vector and the position vector? What is this angle? Any guess? 90. 90. Who says 90? Is that the correct answer? It looks like it, based on my drawing, although it's not perfect. Earth is moving around an almost circular orbit, and these two vectors are almost perpendicular to it. We are going to study Kepler's problem next time, and we will mention about the elliptical orbits, but we can take it as circular. And you must have seen from the harmonic motion or circular motion that the two vectors, the position vector and the velocity vector, are perpendicular if it's a circular motion. So this theta is actually 90 degrees. So the angular momentum of the Earth, its magnitude, is the distance between the Sun and Earth, its mass, times its velocity, its speed. Now you can put in those numbers. This is 1.5 times 10 to 8 or 10 to 11 meters. I don't remember the mass of Earth, and the velocity of Earth, or the speed of Earth around the Sun, is about 30 kilometers per second, which is 3 times 10 to 4 meters per second, and you will find the answer in units of meters, kilogram, meters per second. So it will make it meter square kilogram per second. Now, what is the direction of the resulting angular momentum? Here is the vector, position vector. Here is the velocity vector. So to use the right-hand rule easily, we can just transfer the velocity vector to the origin. We just transformed it here. And now we can use the right-hand rule very easily. Here is the r vector, here is the velocity vector. You just curve your four fingers from r to v, and the direction of your thumb is showing the resulting vector direction. So the angular momentum of the Earth, now not only the magnitude, is whole this thing, I don't know what it is, this whole thing, I don't want to write it again, in the direction of positive z. If this is x, this is y, the positive direction pointing out of the page is going to be the z direction. Now, in the last 2 minutes, we can extend this example to a different system, which is also something we are very familiar with. If you were to determine the angular momentum of, say, Jupiter, that is the biggest planet in our solar system, would you expect to have a larger angular momentum or smaller angular momentum compared to the angular momentum of the Earth? Jupiter is a massive object, so it's going to make its angular momentum large if you just consider the mass of it. Is it closer to the sun or further away from the sun compared to the distance of the Earth? It's further away, one answer is. I don't know the others. Do you know where Jupiter is? How many of you say it's further away than the Earth? Decent. So how many of you say it's closer to the sun than the Earth? So what do you say? I mean, the whole crowd there. It is further away. Now, we are going to put just numbers. Our next question, how about LJ, Jupiter's angular momentum. Let's call it LJ is the distance between Sun and Jupiter. Let's call it RJ. Or let's not just make it vector, cross mass of Jupiter times the velocity of Jupiter around the Sun. So it depends on the distance from the rotation axis, its mass, as well as its velocity, because mass times velocity is the linear momentum. So let's just remember the almost accurate numbers. The distance to Jupiter is about 5.2 times the distance from Sun to Earth. So if you take the distance between the Sun and Earth as 1 unit, Jupiter is 4.2 units further away. So it's almost 5 times more distant. The mass of Jupiter is larger than the mass of Earth. I hope there's no doubt about it. How much larger? Can you make any guesses? 10 times? 50 times? 2 times? 33 times? Almost correct, but not correct. The mass of Jupiter is about 320 times larger than the mass of Earth. And finally, the velocity of Jupiter around the Sun is actually smaller than the velocity or the speed of Earth around the Sun. It's 0.37 times the velocity vector magnitude, because velocity of Earth around the Sun is about 30 kilometers per second. Velocity of Jupiter around the Sun is about 13 kilometers per second. Therefore, we can estimate the angular momentum of Jupiter knowing these numbers. Is it going to be larger than the Earth or smaller? Well, just put them in and see. The answer is the angular momentum of Jupiter is about 615 times the angular momentum, 650 times larger than the angular momentum of the Earth. Now, I dropped all those magnitudes. Is there a reason for it? Namely, the direction of Earth's angular momentum is parallel to the direction of Jupiter's angular momentum. So here is Earth rotating around the fixed point, the Sun. Here is Jupiter, far, far away, but let's put it anyway. It's also moving in the same direction with respect to a fixed point, that is the Sun. So, should the angular momentum direction be the same as the direction of Earth's angular momentum? Yes, why not? Here is the direction of velocity, here is the direction of Jupiter's velocity, here is the direction of Earth's position vector, here is the direction of Jupiter's position vector. So the resulting angular momentum vectors are going to be in the same direction. That's why we can just drop those magnitudes and write that it is just 615 times larger in the same direction, which is, in this coordinate representation, positive z direction. So let's give a 10-minute break. After that, we are going to continue.